Can you hear me on Zoom? Thank you. Yeah. So should we get started? I'm happy to see so many of you, especially for the quiz. Yeah. Maybe I should make the attendance compulsory next time I teach the course. Yeah. How's everyone feeling? How you're good so far? Yeah. With the programming, everyone finished the programming assignments, or some people are still? Yes. I wanted to say about the programming. I'm sorry for the confusion about going back and forth about the late days. So I realized indeed the syllabus was a bit confusing. So and I apologize, it was my mistake. So I rewrote the syllabus. We'll give you 4 late days per assignment. So just to make it more flexible for everyone. Yeah, I hope that didn't cause any stress to those of you who are still counting on those. Let me think. So yes. So for today, we'll run the quiz in the second part of the class. It will be 40 minutes. It will be pen and paper. My TAs hopefully will come around 5:56, and they'll bring the printed quizzes. Oh, sorry. Here you go. I didn't see you. Perfect. So yeah. So we have everything printed. Pen and paper, open book. You can use any materials from the slides. You can use a laptop if you want to see the slides. So no problem on that. Yeah. Okay. Another announcement I wanted to make. So we decided that we will also drop the lowest score on the quizzes. So there'll be 3 quizzes, and we'll drop the lowest one. But that's yes. So it will give a bit more flexibility to those of you who need that. But they are compulsory. So all the quizzes are compulsory. So instead of attendance and doing them and giving your best. So otherwise we will drop the low score among the 3. Okay. How does that sound? Is that good? Is everyone okay? Is everyone happy there? Okay. So let's see. So last time we were talking about Markov decision processes. Can somebody tell me quickly, what does the Markov property say? Let's do a recap. Somebody. Yes. What is independent? The current state is independent from the past. Yes. The current state is independent from the past. That's what the Markov property says. Is anyone still confused about that? Yeah. So somebody tell me quickly, what does the value of a state represent? We were talking in the last lectures. What does it mean in simple words? Anyone from here? What does the value of the state mean? Yeah? How good is the current state? A bit more precisely from somebody else. I know you're answering a lot of questions, but let's hear from other people. What more precisely, how do we measure the goodness of a state? Yeah? We use the Bellman equation to check the other states around it.
The value of the state you're in depends on the states around it,
right? Yeah. And there's something a bit more. So there's something also, we were talking about the expected future rewards you're going to get from that state. Actually, the value, how it's basically given by the expected rewards you will get into the future if you start in that state and follow an optimal path. Yeah, that's what we were talking about the value. What does the value mean? The policy, anyone quickly? What does the policy tell us? That's very simple. Yeah.
There's a
hierarchical. There's a direction on the map. That's what I heard so far. Yeah. There's a table and there's some arrows. No. Yeah. So it's in each state. It tells us what's the optimal action to take to get into a new state. That's what the policy tells us. Yeah. So then we have rewards. Again, we have rewards, we have transitions, and all these other things. And what's a Q value from somebody? Well, what did the Q value represent? Anyone remember?
Is it just the state and action value?
Maybe we have to do the quiz on the MDPs as well. We'll do it in a few weeks. This will be on the quiz. What's the Q value? Let me see. Do I have slides for it? This thing is a Q value. What is that? Somebody. What is that? What does it represent here? What do we have here in this node? Everyone is sleepy today. What are they thinking? Yeah, somebody there. Yeah. State and the action is just a pair of state and action. So the difference, that's just a state. A Q value is a state and an action. It's a tuple of both the state and the action. That's what it means. We'll see shortly why today. If we get there, we'll see why these are useful. These are very useful. These Q values. We'll be able to do a faster inference basically with those Q states, Q values. So 1 sec. Yeah. So we were talking last time about optimal utilities. We were basically again we were saying these are values of states. These are policies. These arrows tell us the policy. What's the optimal action to take? We define what a Q state is. It's again a state and an action, and the optimal policy is basically the optimal arrows that we get. And then we introduce the Bellman equations, which basically give us a recursive formula in the values of a state, which also depend on the values of the state. So it's recursive on the values of the other states around those states, where we basically take a maximum over all the potential actions we can take from this state, and then sum over all. And then we sum over all possible states S prime we can land into, and then we sum over this, which is basically the current reward we get in state S prime plus the expected future rewards, basically, the value. This is basically current reward plus expected future reward into the future. That's what the value means. And we discount it by gamma. Since the rewards are in the future, we have to discount them because they're not coming today. Yeah. Bellman equation is a very important equation. It allows us to do what we'll see very shortly. You can do value inference and policy inference with that, which is here. So value iteration, we'll talk about two things today: value iteration, policy iteration. We saw briefly last time how we can do value iteration. So basically, the idea is we're trying to find the optimal policy. We were saying last time that if we do something more naive, like an expected max search, where we basically take this state and do an expected value over all potential actions, and we recursively go down the tree in a recursive manner, that's not too good. It's basically doing a depth first search in the tree, but that's we keep revisiting the old states, the same states multiple times. It's not a good solution. So you have all these problems that the tree is infinite. Some states appear over and over, so we keep revisiting it. There's a depth first search, basically. If we do depth first search on that, it's not going to work. So instead, we do something called value iteration. We start to like bottom up. We start from all the values, we initialize them to 0, and we estimate the iterations over values, the states. So I showed you last time. So basically, the idea is we start with current values. We start with all values for all the states being equal to 0. And then we calculate the values for all the states for depth I plus 1. So for example, from given vi, the values at depth I, we calculate the values at depth I plus 1. So basically, the values at depth I plus 1, we simply apply the Bellman equation, and here we put the values at depth I, and that will give us a recursive formula in terms of iterations over these values. And we throw out the old vi values, and we keep updating them all at once. So we do a full pass over all the values of all the states on our game. And we repeat this until convergence. And there's a theorem saying that this will converge to unique optimal values, because the approximations get refined towards these optimal values. And one thing we'll see that a policy may converge long before the values do. We'll see shortly. Sometimes even the values keep changing. The actions will converge generally faster than the values, the optimal values. So we showed this example last time on this grid, on our grid. Initially, all the values on our board are 0, apart from the end states. The values in the end states are just the actual rewards, +1 or -1. This is at iteration 1. So then when we do a new step, at iteration 2, the values that are closest to the goal state, like this one, we only have 1, that one starts becoming non-zero. So it actually gets a non-zero value. And then the other adjacent states next to that, afterwards in the iteration 2 will get non-zero values. Yeah. So that's the formula we were talking about yesterday, just a slide ago. And that's our state that got updated. And for example, and this is how they got updated. So the value at square 3, 3, this is 3 on x and 3 on y, this state, this red square, is a sum over all possible states you can land in, given that you'd go right. So this is for an action to go right. So if you go right, you can land in 3 states, right? Because you can have noise. You can land, most of the time you'll end up in this state with 80% probability. With 10% probability, you end up in the blue state. And with 10% probability, you go left, which means you bump into the wall, so you stay there. You stay in that state. Is everyone seeing it? Does everyone see how this goes up? So So we sum over all possible states we can land in. And that's why we have three different terms here. For all those three states we can land in. And this comes up as, so the rewards are, these are the rewards. We have a reward of 1 for the green state, a reward of 0 for the blue state, and also a reward of 0 for the red state. Because we had initially 0, that was the update, 0, 0, and 1. And 0.9, what is 0.9 here? What was 0.9 in our, yeah? Gamma, yeah. So gamma, the discount factor is 0.9, so that's what we have, 0.9 here. This is gamma times the value. So that's, this is after we flip them around, we get 0.9 times, again, the probability of reaching the green state times the reward in the green state, that's the value, so in the green state. Probability of reaching the blue state times the value of the blue state. Probability of reaching the red state times the value of the red state, which is 0. They're both 0. And that's why it gets updated to 0.72. So this thing ends up being equal to 0.72. And that's why we put that here. I'll stop here for a second. Any questions? Yeah? The probability is given by the problem. So the probability, these ones, you mean, the 0.8, the 0.1. So these are what's called the transition probabilities T, and they are given by a problem because, remember, we had the situation with the robot that, let me do it here on the board. So I guess we don't need that. We have a square. So if you go up with 80% probability, 0.8, you'll actually go up. With the 0.1%, you're actually going to go right. And with 0.1, you're going to go left. So 80% of the times you're actually going to go up, 10% of the times you're going to go right, and 10% are going to go left. So these are probabilities that are, they were defined by our problem. This is how we said that the robot works, in the sense that it can make mistakes sometimes. Maybe the engine is not fully tuned. Yeah. Any other questions? So yeah, that's what we had here. Any other question? Yeah. Yeah. And it's already going to the right, because you choose to go right. So the action is to go to the right, but the state you land in will not necessarily be the right, or most of the time will be actually go right. There's some, yeah. But with 10% probability, you'll go down. With 10% probability, you'll go up and you'll bump into the wall. So you stay there, you'll stay in the red state. Yeah, does that make sense? Okay, so in general, the behavior would be that, and then if we do another iteration, a second iteration, these other values adjacent to the non-zero value, so we have two neighbors here that are adjacent to this. These neighbors will become non-zero now in the next iteration. So they'll have, and this will keep happening up until all the squares will become non-zero, basically. And we saw this in this diagram. There was the last thing I showed yesterday. So initially everything is 0. We initialize the values of the goal state, and this is the negative goal state. After one iteration, we get this one 0.72. After 2 iterations, these ones become non-negative. After 3 iterations, these ones also become non-negative. These ones, notice how these ones keep increasing in value. They haven't converged. So this one keeps modifying, keeps increasing its value to 0.78, 0.83, 0.84, and so on. So those ones will still keep accumulating value over the iterations. But can you tell me why? Why this is happening? Why does this one keep accumulating value? Yeah. Yes. Yeah, so then because you can end up with, by mistake, of course, even if you try to go right, you can still end up going down. But then initially you thought this one has 0 value, but later on you realize actually this one has some value and it keeps increasing. So then that's why the value of this state also keeps increasing. So they all influence each other. That's the whole takeaway. Yeah. And we keep running it up until not all the squares in the game become non-zero. And you see they keep increasing in value, increasing up until they eventually converge. So after 12 iterations, they almost converged. After 100 iterations, they definitely converged. So yeah. And you notice these arrows represent the optimal actions in each square. So it's the optimal action here is to go up. The optimal action here is to actually go left and go around this block. So it shows the optimal policy. The policy. So yeah. So there are some important observations to make about the convergence of this. So the main question is, does this converge? Does this value iteration converge? And the answer is yes, it does converge. So if we define what's called the maximum norm or the L infinity norm, like this, have any of you heard about LP norms? L1, L2, L infinity? Some nods. That's the formula for the max norm. So basically, you have a vector U. So you basically take each element and take the maximum over S, and that's basically going to be the L infinity norm. And there's a theorem that says for any 2 approximations U and V, so these U and V are approximations to the values of our board. So for example, the different approximations, then we have this thing that holds. The difference between U and V at iteration t plus 1 is more than or equal to gamma times U and V, difference between U and V at times t, at times the t. So which means that any distinct approximations, if these are 2 different approximations, then they get closer to each other more and more as more iterations come. So any approximations end up getting closer and closer and closer. So eventually this means that they will converge to a unique, stable, and optimal solution if they get closer and closer. Does somebody know why they converge from this relation? Any ideas why? Let's see. So I suppose none of you took a real analysis class, right? Because yeah, most of you are in computer science. Yeah. So there's something you can do about it. It's actually not too complicated. So we rewrite that expression like this. So U t plus 1 minus V t plus 1 divided by, so we take the right hand side and put it here, divided by U t minus V t in norms. And this has to be smaller than or equal to gamma, right? So I just took that expression and wrote it here. So there is something we can do on this, which is that we can rewrite this as U minus V. We can rewrite it as a W, as a different sort of vector, basically. So if we define that W equals U minus V by definition here, then basically this becomes the norm of W at iteration t plus 1 over the norm of W at iteration t. and this is less than or equal to gamma. Does somebody know, has somebody seen this before? And does somebody know what would happen if you have this this criterion like this? We have a sequence, a series W at t+1 over W at times t in absolute form. So I can even write it. I can take out these and maybe even rewrite them like that. Although that's a bit more, yeah. Let me not do that, but for now. So this is what's called a ratio test. If some of you have heard of this, it's a ratio test. It's in reanalysis. Basically, if you have a series that that obeys this criterion, where this divided by that is less than or equal to gamma, which is a number between, which has to be smaller than 1. If this gamma is less than 1, then we know by this ratio test that this will converge. This series will converge. So so this is called a ratio test. So if some of you might encounter this. It's so sometimes I know this is a bit more sophisticated, but if you want to do sometimes more sophisticated AI, it helps to know some maths, some of this mathematics, because this is how you get these results. And there was something more here. Yes. And there's another theorem that says that if we have the same approximation, but we calculate the difference between these approximations at different iterations, so this is a t+1 minus the values at times t, and if these get smaller than an epsilon, they get arbitrarily close, then basically the difference between our approximation and any approximation u, including the correct one, the correct approximation, that will become arbitrarily close. So basically what this means is that our value estimations will become closer and closer to the true estimate. So sorry, to these ones, this u. These ones will be the true estimates. So that means our algorithm will converge to the true value estimate based on this. Yeah. Okay. So computing actions. So which actions do we choose from these Bellman equations, given the optimal values? Now that we have the optimal values, we call them V star. Which action do we take? Anyone? The one with the highest value? Yeah. But actions, so values correspond to states. So values are always corresponding to states, not to actual actions. So with actions, you don't assign a value to an action, more you assign a value to a state. So so what we do is that we literally run the Bellman equation forward once, and we take the action that maximizes this formula, which is this probability of transitioning into state S prime, and then the reward of state S prime times the discounted value at state S prime. So we do that for all the possible states, and then we do the same for all the actions, and then we take the action that maximizes this formula. Yeah, so that's how we choose the optimal action. What about how do we choose the actions given Q values? So given Q values, we simply take the maximum over the Q value of a state and action. So remember, the Q value was giving a state and an action. it's like a value of that. So then we simply take the maximum, the action that maximizes that. So this is the reason why these Q values are important, because here when we try to find the actions afterwards, we don't have to do this more complicated expression. We just extract them out from the Q values. You'll have a table of Q values for different state and actions, and you extract the one that has the maximum value. It's much simpler. So the takeaway is that actions are easier to select from Q values. That's the takeaway. That's why we need them. There's another concept in which we can calculate utilities for fixed policies. And these policies don't have to be optimal policies. They can be non-optimal. Like, for example, I have a policy, some actions that are fixed and predefined that are not necessarily optimal. And you can still compute values for these policies. So we can define the utility of a state S under a fixed policy pi that is non-optimal as the same way as before, as the expected discounted returns by starting in that state and following now this non-optimal policy, following what the non-optimal policy was telling us. So our values are now given under a particular policy pi, and we run the same Bellman equation where now the values, again, values of a state S under policy pi is a sum over all the states we can land in after taking an action that is given by a policy pi of S. Yeah, so now the action is given by this particular policy. It can be a non-optimal policy. It can be quite far away from optimality, but we can still compute, the mathematics still works out. You can still compute the values under this policy. And they will be different from the values under the optimal policy. But the mathematics allows you to compute them equally easily. Any questions here? How do we compute the values for a fixed policy? So the same thing as before. So we initialize all the values initially now under this policy to 0. And then we run the Bellman equation where we do multiple iterations. So we start with values at iteration I plus 1 are given by the values at iteration I, and then we run through this equation again. And that's how we keep getting new iterations of these values. It's a linear system, and yeah, it's simple to compute. So there is a problem with value iteration, and the problem is that it's very slow to consider all these actions every single time, and actually doing this summation over all these states and take all these actions and so on. So even here, so considering all these actions and summing over all the states, it's very expensive. So what we can do is that we can do something called policy iteration, which basically what it does is that we calculate the utilities for a fixed policy for a certain number of iterations. So we fix our policy pi. We do several iterations of value iterations, like update the v's, the values multiple times, and then we update the policy afterwards in step 2. We improve the policy. We do one step of the policy iteration, and then we do multiple steps of the value iteration. And this is a much better approach, and it results in faster convergence than before, than just doing value iteration. And we repeat the steps until the policy converges. So graphically, this will be, you do, let's say, a policy iteration P0, then you do a value iteration V0, V1, V2, V3, several, and then you do a new update on the policy. You get a P1, and then so on. Then you get a V4, do some more value iterations, V5, V6, and then you get update the policy again. You get a P2, and so on. So you interleave policy iterations with value iterations, like this. Yeah.
Yeah, that's not the policy.
And the values, both. So this will be value. Yes, this will be the offline the optimal policy and the values under the optimal policy. Yeah. Any other questions? Yeah. So that's what this is saying. So now this is the update. We have a fixed policy pi, and we find the values with this simplified update. So our policy is that it is pi k at iteration k. So for example, if we're at this step, this will be pi 1. So for example, this will be v4 pi 1, like this. This will be v4 v0 under pi 0. This is v0 under pi 1, under pi 2, under pi 3. No, sorry, this is 0. All of them are 0. And this is pi 1, pi 1, pi 1, like that. So for the policy iteration k, we keep doing value iterations, multiple of these. And then we do policy improvement. We update the policy from pi k to pi k plus 1 by taking the maximum finding for each state. We find what is the best action we take under the Bellman equations, given the last estimate of the values of the states at iteration I plus 1 and under policy pi at iteration k. We flip updating one and then the other. So in value iteration, in every pass we update utilities and policy. But it's just they're more expensive to do with value iterations computationally. But in policy iteration, we can do several passes of utilities with a frozen policy, and then we do sometimes occasionally occasional passes also on the policy. Like here, you see, we do much fewer policy updates than we do value updates. Okay, so to sum up, these MDPs are a very powerful formulation to solve such problems. We can compute values, we can compute optimal policies, we can plan under uncertainty. We've seen how what Q values are, how we compute optimal values and optimal policies. And mainly, this is a form of, I should have mentioned, this is a form of dynamic programming, actually, because we first compute the sub-problems, and then based on sub-problems, we can compute newer problems based on the sub-ones. We never recompute the same problem twice, as we would have done if we have done a depth-first search, for example. Yeah, okay. Let's get the quiz ready, right? Oh. Yeah. Okay. Oh, yeah. Did everyone finish? Did everyone write their names? Yeah. Sorry. No, just on the top, on the front page. That's it. Okay, then I guess we can get started. Yeah. Okay. Let's start. So we have 40 minutes, and yeah, I'll set up until 6:45 sharp. Yeah.
Does the Roomba question mean that they're like on top of each other, or that they're each in one?
Um,
Is that okay?
oh, yeah. Well, yeah, he left. He left. Yeah. Yeah, I think there's a mistake in D because it needs to have directionality. Right? These are consistencies. It needs to have. It basically needs to have a directional graph, right? I actually learned it for this class, so I'll double check with him.
Hey, Raz, you're not mute. Yeah.
Oh, yeah. Thanks. Sorry. Aditya, are you still working on your quiz or are you done?
Oh, I'm done, Professor.
Sorry?
I'm just about to leave. I've finished. I've turned it in.
If it's an okay, perfect. Well, that's great. All right, you say you feel free to leave. Yeah, I'll be closing the Zoom. Yeah, also.
Okay, thank you.
There's nobody else. Okay. Fateme, are you still
Yeah.
there?
Yes. Do
So
you
I
need me?
was talking to Swati here, who's next to me. So what I was saying is about grading. I'll check if I can hire a second grader. So because right now we have Brian, and if that's the case, then basically Brian and the second grader can do the grading on the quizzes. Yeah. So in that case, you won't need to do the grading on these.
Okay.
And yeah, so I'll be in touch with that. If not, I'll need some help from you and Swati to do.
Okay. Yeah.
Okay.
Sure. Yeah, sure.
Okay. That's it. As I want to say, and I'll take these quizzes, so they'll be in my office, and I'll be in touch. To let you know.
Okay. Okay. Yeah. Sounds good.
Okay. All
Thank
right.
you.
Take care.
Thank you.
Bye.
Yeah, you too. Bye.